Bismillahirrahmanirrahim. My dear students, in this lecture, our goal is uh, uh, to to apply the domain decomposition method on some physical shapes or physical problems. Here in this lecture, we have a fluid phenomena, a physical problem in fluid dynamics, and we are trying to uh, solve that physical shape or physical phenomena using the domain decomposition method and predict the physical structure or the changes in the physical structure using this domain decomposition method. So here we have an example from the book of Papanazzo, viscous fluid flow. The example is transient Planck flow. This is a physical phenomena. Uh, what happening in this example? In this example, we consider some liquid, some Newtonian liquids, which has density rho, and the viscosity of the liquid is eta, and this Newtonian liquid is bounded by two long infinite parallel plates, and the distance between the parallel plate is h. Uh, and we also assume that the liquid between the two plates is initially at rest, and at time t equal to 0 plus means when the time is increases start from 0, the lower plate of this physical structure is suddenly brought to a speed velocity v in its own plane, or in other words, we applying a sudden force or jerk on the lower plate, and the lower plate starts moving with velocity v, and the upper plate is held stationary. So if you model this physical phenomena using all the fundamental equations, Navier-Stokes equations, the continuity equations, so in hand we have in a result is exactly this one, and this is exactly that heat equations as we discuss uh, in previous lectures. In previous lectures you already discussed the homogeneous linear PDEs and the inhomogeneous linear PDEs. So now this is exactly that heat equations, or but the space variable here is y, and time is also involved in this heat equation. So now for this heat equations we have these boundary and initial conditions. Now, is this homogeneous or inhomogeneous? This is exactly a question. So you need to know that either it is homogeneous or inhomogeneous problem. So this is I'm left this problem to you, that you need to know that what is exactly the nature of this PDE. It is linear, it is homogeneous or inhomogeneous. But I claim that this is homogeneous problem. Okay, so for this problem, uh, we have these two boundary conditions. These are exactly the boundary condition, and one is the initial condition. So here we have these two are the boundary condition of the problem, and this equation or this boundary is called the initial boundary condition. By initial you mean that when you start from the initial position where t is 0. So this is exactly the initial condition, and these are the boundary condition for the above transient Planck flow, and this is heat equations. Now What exactly the scenario of ADM, or what is the basic fundamental technique of the domain decomposition method? The first step is we recognize or we identify the linear operator. So here you have the choice if you uh, want to choose the linear operator L of t, so this is your choice, or if you want to choose the linear operator L of x. So for L of t, if you want to choose this, the linear operator L of t, so for this L of t, you need to choose, or we need, we assume that this is invertible, and this is equal to exactly L inverse minus 1 is equal to integral of the unknown function with respect to t dt. So then the invertible operator will be this one. And if you want to choose the linear operator in terms of x, this is Lt is equal to partial by partial t. And if you want to choose this Lx is equal to partial by partial x, or partial square by partial x square, because sorry, this is y, sorry, this is y, because we have the space variable in this equation is y, so this must be y. So partial square by partial y square. So for this we have the linear operator. If this is your linear operator, then we assume that this linear operator is invertible and the integral exists, and the double integral which start from 0 to h, and this is basically the boundary for this one is 0 to h. You can take exactly in this fashion, 0 to h. 0 to h is another boundary of the unknown function. The unknown function is ux of yt. U is depending on y and t of dy and dy. So this is the invertible operator, which is assumed to be the invertible operator for the linear operator L of y. So now this is exactly the first step of the domain decomposition method. Now what is exactly what ADM do with the PDE? Once you decide the linear operator, then the assumption is that linear operator is invertible. So we apply, first of all, the first step is we rewrite this heat equations in operator form. L of t of u of x, y of t, nu is constant, which has value rho by eta. I think this nu is equal to the division of, or the ratio of this density and this viscosity. And this is L of x, u of y of t. So in the first step, in the next step, we applying the linear operator on both sides of this equation, the invertible operator, sorry, the invertible operator on both sides of the equations, and we say that this is invertible, so then u of x of u of y of t is equal to the source term or the zeroth order solution. This is zeroth order solution, which comes from the integration of the boundary condition plus L inverse t of L of x into u of y of t. So the equation reduced to exactly this form. Now, where there is unknown function u, transform that unknown function to the series form, or plug in u, the series of this u in this equation. So once you plug in the series, then this equation reduced to the series form, and once it is in series form, then expand the whole series on both sides of this equation, then you will have an equation like this one. u naught plus u1 plus u2 and so many more term is equal to uh, many more term is equal to the zeroth order solution. This is your job to calculate, plus the double integral and the expansion of the series here as well, u naught plus u1 plus u2. So u naught is equal to this one. This is exactly the value of u naught, and u1 can be calculated from here, and gradually or iteratively you can calculate each term of these equations, and then sum up all the terms or substitute the values of all the segments of u naught, u1, u2 in this form, in this equations, and simplify the whole terms, the whole series. That simplified form will be the exact will be the solution of this heat equations by using the ADM method. This problem is solved by uh, separation of variable method of separation of variables, in which what they are doing, they exactly choose this u of x y t in a in a two single variable, the decomposition of two single variable, and further they step by step they solve this method by using this separation of variable method. Now is this was your assignment in previous lecture as well, and that you need to calculate the solution of the heat equations using the separation of variable method. So here is exactly the solution, or the solution of this heat equations by the separation of variable method is exactly, it exists here, it is calculated here in this book. You can see here, this is exactly the solution of this equation using the separation of variable method. So now you need to calculate or solve that heat equations by using the ADM method, and compare your ADM method or the solution of ADM method with this solution. So you can easily then decide that which method is the best method, and how you can compare both the solution of the